Let's start on section 1.8. The topic is absolute value, and in particular, our goal is to solve equations and inequalities that include an absolute value in them. So for example, if I have the absolute value of 2x plus 1 is equal to 7, then how do we solve that for x? And we could also consider if the equal sign were replaced by a greater than or a less than, then we'll learn how to solve those as well. So first, the definition. The absolute value measures the distance from 0 to a number a on the number line. And so I've drawn a little number line here, and let's just work a couple of examples. So if I ask you what is the absolute value of 4, then you would say, well, what's the distance from 0 to 4 on the number line? And you could just count over 1, 2, 3, 4, and so your answer is 4. And if I ask you for the absolute value of -2, then you're going in the opposite direction from 0. You're going over to the left, but distance is always positive for us. We're talking about an undirected distance. So the direction that we go, whether we go to the right or to the left, doesn't matter. We can just count over 1, 2. And so when I take the absolute value of any negative number, all I'm doing is I'm just dropping off the negative. So for this reason, sometimes we say absolute value of A is always positive. And that's mostly true, except if you think of the absolute value of 0, which of course is just 0. So with that brief introduction, let's go on and let's look at some examples of some basic equations and inequalities. And from these examples, we'll develop some rules that we can apply to more complicated examples, like the one I gave you up here in the corner. So the first example is absolute value of x is equal to 3. And so I bet you can think of two good answers for that. I bet you would say that x could be equal to 3, or x could be equal to -3. And of course, you could just plug in either one of these values into the equation to check that it's correct. And of course, well, maybe we should do that. Let's just go ahead and check real quick. Check x equals -3. And so just plug it in and ask, is that true? Well, on the left-hand side, we can simplify. We can drop the absolute value and drop the negative along with it. The absolute value of -3 is 3. And so, yes, that worked out. Okay, so the generalization that we want to make, the rule that we want to write, is to say that if the absolute value of x is equal to a, then x is equal to a, or x is equal to -a. And when we write this rule, x is a variable or it's a variable expression. So in just a minute, we'll replace the x here inside the absolute value with something a little more complicated, like 2x plus 1. And then over here on the right, a is a constant. A is just a number, like 7 or 3, and a does not have a variable. There is no variable over on the right side of this rule. And there's one more thing that we should note, which is that in this rule, a must be positive. And if a were negative, then that would be a special situation. Maybe you can see right away that there's no solution if the number on the right there is negative. But we'll talk about that a little more later in the section. Okay, well, let's go on and let's see a couple more rules. We can look at this next example here. Absolute value of x is equal to the absolute value of 3. And I bet you would say once again that the solutions are 3 or negative 3. So let's go ahead and write the rule. Let's write if absolute value of x is equal to the absolute value of a, then x is equal to a, or x is equal to negative a. And this time the a is just a little bit different than in the first rule. So in particular, this time a doesn't have to be positive because it has the absolute value around it. And for that matter, a doesn't even have to be a constant. A could be another variable expression. So that's a small detail. We'll see it again when we get to some more examples later in the section. So let's go on to example 3. We have the absolute value of x is less than 3. This is a little bit trickier than the equation because there are an infinite number of solutions. And so we need to use inequalities to write the solution, or we could use interval notation to write the solution. So before we do that, let's just try to think about what some solutions are. So I would ask you, can you think of a number we can plug in for x and make a true statement? And I bet you would say that 2 seems like a good number, and 1 seems like a good number, and probably 0. And could you go lower than that? Does negative 1 work? Does negative 2 work? They do. They work. You can check them. Does negative 3 work? Well, let's come out here on the side and just check x equal negative 3 in this inequality. So let's plug it in and write a question mark at the end. Let's simplify the left-hand side and get 3. Is 3 less than 3? No, that's not true. So negative 3 doesn't work. Negative 4, negative 5 don't work. Maybe we should go back to the positive numbers and ask, is there a larger, can we go larger than 2 and still have a solution? And sometimes students say no because they think of 3 and 3 doesn't work. But then oftentimes I'll have a student say, well, what about 2.5? And then I'll say, can you get larger than that? And you might say yes, 2.9 or 2.99 or and so on. And then similarly, at the left end of this list, you could have negative 2.5, negative 2.9, negative 2.99999. And so here's a list of solutions that hopefully inspires us to write a little 3-part inequality to say that x, the value of x, is between 3 over here at the right end and negative 3 over here at the left end. So we're going to say negative 3 is less than x is less than 3. X is between negative 3 and 3. And of course, we just studied the 3-part inequality in the previous section, and now we're using it here to write the solution to this absolute value inequality. Okay, could you write this 3-part inequality in interval notation? I bet you could. I bet you would write negative 3 comma 3 with parentheses around it. So a three-part inequality and then the interval notation, both are good. Okay, so with that, let's go ahead and write the rule. Let's say if the absolute value of x is less than a, then negative a is less than x is less than a. So hopefully that three-part inequality that we just wrote for the rule matches in your mind what we wrote for the little example we worked over here on the left-hand side, right? We know that x has to be less than a, but x also has to be bigger than negative a. There's one more thing we want to say. We want to say a is a constant and a is greater than 0. If a were less than 0, then we'd have a special case that we'll deal with later in the section. Okay, one more example here, and then we'll have all our rules worked out. So this time we have absolute value of x is greater than 3. So once again, let's try to write out some numbers that satisfy this inequality. You would think of 4 and 5 and 6, and you could get a lot bigger. You could get 100 and so on. And then how small could you go? Could you go lower than 4 and still have a positive number? You could. You could have 3.5 or 3.1 or 3.001, for example. And so all of those are good answers. And you would write that as x is greater than 3. There's another possibility, and that is that you could have a negative value of x that still satisfies this inequality. Can you think what it would be? What about negative 4? Would negative 4 work? It would. Negative 5, negative 6, negative 100, and so on. And you could even go higher, go larger than negative 4. You could go negative 3.5 or negative 3.001, for example. And so then this list of negative solutions could be written as x is less than negative 3. X is less than negative 3 or x is greater than 3. We could write that in interval notation. We could write negative infinity up to negative 3, and then a union symbol, and then 3 to infinity. So for the rule, we'll write if the absolute value of x is greater than a, then there are two possibilities. The first possibility is intuitive, I think. It's to just drop the absolute value and just say, well, x is greater than a. And the other possibility is less intuitive, but you could also say x is less than negative a. And of course, this rule follows from the example. In the example, we had the number 3, and in the rule, we have the constant a working just the same way. We should note that for this rule, a is a constant. A does not have a variable in it, and a is greater than 0. If a were less than 0, that would be a special case. Okay, so let's go ahead and do one more problem before we stop this video. Let's come back to the let's come back to the problem that I suggested at the beginning of the video. It was the absolute value of 2x plus 1 is equal to 7. And so you could look at your 4 different rules, and you would recognize that that this is the first rule, where you have in the first rule a variable expression inside absolute value on one side and a constant over on the other side. And so that's what we have in the example. The rule says we need to get 2 equations. We can drop the absolute value and have x equals a or x equals negative a. So the variable expression inside the absolute value, 2x plus 1, is equal to the number on the other side of the equation, or 2x plus 1 is equal to the opposite of that number. And then we can just solve these 2 equations separately. We can subtract 1 on both sides and get 6, and we can divide by 2 on both sides and get our answer 3. And then we can do that again. This time when we subtract 1, we get negative 8, and then when we divide, we get negative 4. And so here are our 2 answers. And we can put that in set notation as well. Notice that's different than interval notation, right? The braces mean just the number 3 and just the number negative 4, and not the numbers in between those 2 numbers. That's different from the parentheses and the brackets that we're using to express intervals. Okay, we'll see some more examples in the next video.